Hi, everybody. Welcome to today's live stream on getting started with Simulink on our MATLAB YouTube channel. My name is Tianyi. I am a product marketing manager here at MathWorks focused on Simulink and model-based design. Joining me on the session today is my colleague Ashwin. Hey, Ashwin.
Hi, Tianyi. Hello, everyone. I'm Ashwin, and I work in product marketing group at MathWorks, and I work in model-based design and Simulink. So today we are gonna have 1 hour presentation on Simulink, and during this presentation, we are gonna take your questions. So please feel free to pop your questions in the chat window. And maybe before getting started, Tianyi, you would like to tell us what we are going to do today and how we are going to drive this.
Yeah, so we'll first provide you with an overview of what Simulink is, and then we will step you through some demos and examples to show you what you can do with Simulink to help you quickly get started. Whether you are a student who's taking a course that has a Simulink component to it, or if you're an engineer who's just starting to learn about Simulink and trying to apply it to your current or next engineering project. So regardless of who you are, we think that there are definitely some useful tips and tricks for you to take away from today's session. And just before we wrap everything up, we'll show you the additional links and resources to help you learn more about Simulink. So in terms of today's demos, we'll first show you how you can build a DC motor model in Simulink by describing its electrical as well as its mechanical characteristics. And then we'll show you how you can build a controller to control the output speed of the DC motor by implementing the PID control technique. And then finally, individual components like the DC motors into a larger scale system, such as the package delivery quadcopter drone. The drone has 4 propellers that are powered by 4 individually controlled DC motors. And we'll show you how you can simulate this entire system in a 3D virtual environment. But before we jump right into the demos, I want to take you to the Simulink product page on mathworks.com. So here we see that Simulink is a block diagram graphical environment that you can use to design systems across many different domains. For example, the electrical and mechanical domains that we just talked about with the DC motor. And you can also design systems in other domains like thermal, hydraulic, fluids, and many more. And what's really powerful about Simulink is that it enables what we call model-based design. So if we take a closer look at this diagram here on the right-hand side, there are 2 major components to model-based design: modeling and automation. With modeling, you build a virtual model of your system before you implement it on hardware or build out a full physical prototype of your system. With these virtual models, you can quickly try out new design ideas, explore the design space, and then optimize the system behavior virtually before you take it into the next stage of your development process. So to give you a concrete idea of what modeling really is, let me show you an example of a real-world engineering challenge, that is building the wind turbine. So building a physical wind turbine can be a very time-consuming, costly, and sometimes even dangerous process. And this process can take somewhere between 6 months to even years to complete. But with Simulink, you can start designing the control algorithm of the wind turbine without even first having access to the physical prototype. You might be wondering, how do we do it? Well, in Simulink, you can model the different physical components of the wind turbine, such as the blades, the gear assembly, and the tower. You can model the environment in which the system will operate, such as different wind conditions. And you can test out the system under different scenarios by connecting the wind turbine model to the electricity grid model to see how the system behaves across different situations of electricity supply and demand. And you can rapidly iterate through your control design because Simulink provides you with a fundamental set of building blocks and design tools for you to model complex decision logic in state machines, or for you to lay out your control algorithm in block diagrams.
So Tianyi, I can see a controller there. So once I design my control logic and build that controller in Simulink, How do I generate my code from that? Because if I want
Mhm.
my code to be flashed on a hardware, how would I do it?
Yeah, so that's where the automation part of model-based design comes in. With Simulink and its add-on coder products, you can automatically generate code from your virtual models for your software implementation on different supported hardware platforms, whether it's microcontrollers, GPUs, industrial controllers like PLCs, or FPGAs and ASICs devices. And we write the code for you so that you don't have to write thousands of lines of code by hand. And this really helps eliminate a lot of the manual steps and potential errors associated with the hand coding process. And before you deploy your system into the final production environment, you would like to ensure that there's a good level of quality and safety of your system. So Simulink provides you with a set of validation and verification tools for you to automate that testing process as much as possible so that you can catch design issues early in the process rather than late when the issues are more time-consuming and expensive to fix. And since Simulink is such a powerful tool, it has seen wide adoption across many different industries, spanning applications from wireless communications, electrical technology development, control system design, autonomous systems development, and you can even integrate AI algorithms such as machine learning and deep learning models into your Simulink models for running system-level simulations.
Thanks, Tianyi. That was a great intro. Should we start with our model?
Yeah, let's jump right into the demos and see how Simulink works in action.
Yeah.
So here I have, the MATLAB window open, and there are two ways for me to access Simulink from MATLAB. I can either type in Simulink from the MATLAB command window and just hit enter, or I can just click on the Simulink icon to access Simulink. So here we're seeing the Simulink start page, and it's showing me 3 tabs. On this current new tab, I'm seeing a set of Simulink templates. So templates are skeleton models that have some basic elements like the blocks and connections already laid out for me that help me get started with building my model. And we also have this examples tab where it's showing me examples that are fully built out systems that are reference designs across many different applications and domains. For example, if I'm working on aircraft modeling, I can have access to the examples from the aerospace block set. I have applications from audio signal processing, automated driving, among many others. So these examples give you a great head start for solving your specific problem using Simulink. You don't have to scratch your head over a blank canvas, and instead you can just use these examples as great starting points for you. And we also have this Learn tab, where it's pointing you to all of the on-ramp courses. So these on-ramp courses are free, self-paced, and online-based courses that guide you through a series of exercises for you to hone your modeling and simulation skills with Simulink. So these are great resources for you to learn Simulink. And since today...
Just one more thing, that all these resources are free to use. So they are not for any paid, they don't have any paid subscription to it. So please feel free to use them. Yeah.
Mm-hmm. Yeah, the courses are amazing resources for you to get started. Since today we're building a DC motor model in Simulink, and a DC motor is an electromechanical system, I want to see if I can find a template that can help us build our model. So let me just start typing ahead and see if there's an electrical template that I can use to create the model. And indeed, I found one, and let's just create the model from there. So now we're seeing the electrical template that already has some basic elements laid out for me. I'm seeing some blocks and some connections. But before I jump right into what these elements actually represent, I want to call your attention to this blank space that we have here. This is what we call the Simulink canvas, where you can quickly bring different blocks into the Simulink canvas and then start connecting these blocks to build out your model. And since I'm just getting started with Simulink, I want to be able to browse through the different blocks that I have access to. So I just launched a library browser, which is showing me a comprehensive list of all of the blocks that I have access to, whether it's from Simulink or from the different add-on products. And since we're building a DC motor model, I want to see if Simulink already has a pre-built component for me. It's called the DC motor. So I can perform a quick search from the library browser, and it's showing me all of the best bets based on the search keywords. So what I can do is I can just quickly click on it and then drag and drop it onto my Simulink canvas to bring this block in. And if you have some previous experience with Simulink and you note this block by its name, you can also do what we call predictive quick insert, where you can just double click on the Simulink canvas and then you can type ahead, say DC motor, and then Simulink will show you all of the suggested blocks for you in this list. So we can also insert blocks that way. And yeah, so if I'm someone who's seeing this block for the first time, I might be a little confused about what this block actually represents, right? But there is no need to panic because help is always just one click away in Simulink. So you can right-click on this block to bring out the help section, which will automatically take you to the Simulink documentation on this particular block. Right? So we can see that the DC motor block comes from the Simscape electrical library. Yeah, so Simscape is an add-on product to Simulink that is really useful for modeling physical systems. What's really great about Simulink is that it provides a comprehensive set of pre-built physical components that already encapsulate a lot of the math and physics that describe the detailed behavior of the system that you're building. For example, in this description section, I can see that there are all these differential equations that govern, the electrical as well as its mechanical characteristics of the DC motor. So I don't have to, derive these equations by hand, and instead I can just rely on this block to build out my full system.
So I don't need to model any of the equations. Everything is pre-built inside the block.
Yeah. And so you did mention that there are two different colors in this block.
I was wondering why do we have
that? In Simscape, we use different colors to denote connections and components from different domains. For the DC motor block, the blue denotes the electrical domains, whereas green denotes the mechanical domain. And you can see that there are the positive and negative terminals on the electrical side. So with Simscape, you can lay out connections between different physical components in schematic diagrams. So this is a very intuitive representation of the system that you're building. So I can just connect the negative terminal to the electrical ground that was provided for me from the electrical template. And I want to be able to specify a voltage source for this DC motor. So what I can do is to bring in a controlled voltage source. And this allows me to specify a numeric input as the voltage level to the DC motor. And I do want to call your attention to this top portion here in the Simulink interface. This is what we call the Simulink tool strip. So the tool strip provides you with all of the menus and options that help you discover different things you can do in Simulink. And what's really nice about the tool strip is that it shows you what you need when you need them, which means it understands the context of your work. So if I go to the Format tab and I highlight this block, I can see that once I've highlighted the block, there is a new set of options for me to rotate this block. And I can make my connections very easily that way. So now I've almost completed the the electrical side of things. And now let's take a look at the mechanical side. So I can see that there are these two ports in a mechanical domain. And if I go to the documentation again, there's a dedicated section for me to look at what do the ports represent. So we can see that C represents the motor's case and R represents the motor's rotor. So similar to what we had in the electrical domain, so we had the electrical ground as the electrical reference. In a mechanical domain, we also want to have a rotational reference so that we can specify a fixed point in space to connect the motor casing to this fixed point. So in order to do that, we can quickly bring out a rotational reference to connect to the motor casing. And in order for me to measure the output speed of the DC motor, I would need a sensor. So there are virtual sensors from the Simscape library that we can use here. And there is a rotational motion sensor for us to measure the output speed of the rotor. And again, looking at this rotational motion sensor, we have three different output ports that are denoted by different letters. And to understand what these letters represent, we can again go to the the documentation on this sensor, and we can see that W stands for the angular velocity, which is exactly what we want to measure for the output speed of the motor. And then we also have the positional output, which we don't really care about in our particular case. So Simulink provides you with different options for you to not only capture the signal, but also visualize the simulation outputs. So we can see that there is the scope block from the electrical template. And I can simply connect to the angular velocity output to the scope block for me to visualize this signal. And a scope block is a quick and easy way for you to visualize Simulink signals. And if I double click on it, it opens up a separate compact window that has the look and feel just as the benchtop oscilloscopes that you would see in your engineering labs.
Tianyi, I can see that you have used PS Simulink converter. So is it absolutely necessary to use it every time whenever we use a scope?
Yeah, the reason I'm using the converter is because in Simscape, the signals denote bidirectional energy flows between different physical components. Whereas in Simulink, the signal lines represent data flow, which is single directional. So whenever we go from the Simscape world to the Simulink world, or vice versa, we need to use the converter. But it's a painless process. You just drop this converter in, and Simulink takes care of the conversion process for you.
Okay.
And since we're not really using the positional output, I can just adding a terminator block to signify that we're not really using the value from this port. And looking at the C port on the motion sensor, I have very little idea of what block should I connect this to. So what I can do is that I can extend the connection from this port, and I can double click on a node. And so Simulink is providing a list of compatible blocks that I can connect this output port to. So these are hints and cues for me to understand how I can finish building that part of the model. And on top of this list is the mechanical rotational reference. So it's giving me a strong suggestion that I should also connect the sensor to the mechanical rotational reference that I just connected to the DC motor. So what I can do is that I can simply, flip this block horizontally and then connect the output port to the rotational reference that way.
So I just want to give a call out. Please pop your questions in the chat window. We'll be taking questions along the live stream.
So since we're doing a time domain analysis and not doing any frequency analysis, we can just safely discard the spectrum analyzer from a model. So now,
Tianyi, I just one more thing. I can see a solver configuration block on the left-hand side. Yeah. Do I need to worry about it?
Yeah, so the reason we have the solver configuration block for Simscape models is that Simscape uses a different solver technology from the one that's been used in Simulink. So we do need to have this block here to complete our Simscape model. But we can just stick to the default configurations for our case.
Oh.
And we've almost completed building the DC motor model, but this is a virtual model. How do I make sure that the characteristics of the virtual model match what I would expect from a real world DC motor provided by a particular manufacturer? So this is why we would like to perform parametrization on this DC motor model. And here you can see that there's a list of motor parameters from our documentation. And you can think of it as a spec sheet that you would get from a DC motor manufacturer. And in the spec sheet, you can see that there are different parameters associated with the electrical torque characteristics as well as its the mechanical characteristics. So a nice thing about Simulink Canvas is that I can just highlight this text block and I can do a quick drag and drop right into my model as my model annotation. And it has even preserved all of the original formatting of the text, which is really nice. So what I can do is I can double click on the DC motor block, and it's showing me a list of different parameters that I can change. In this case, we're parameterizing this model by rated load and speed. And I can type in the rest of the parameters to make sure that these parameters match what we have in the spec sheet. So we have a rated supply voltage of 12 volts. And we also have the mechanical characteristics. I do want to make sure that the units match up.
So once we get our matching answers with a real world motor, we can be very sure that we have successfully built our model.
So now I've parameterized the DC motor, and I would like to run simulations to do a quick sanity check of whether we've modeled and parameterized the DC motor correctly. So at this time, I need a stimuli to drive the model behavior. So for this particular case, I can bring in a step function as the source, and I can give it a more descriptive name. Let's say voltage in the units of V. And since we know that based on the spec sheet, when we supply a 12 volt voltage to the DC motor, it's going to achieve a no load speed of 4,000 RPM. So we can specify the final value of the step function to be 12. And now we are ready to run our simulation.
So we are looking for 4,000. Okay, that's we have missed our mark by far.
Yeah, I guess there is about a factor of 10. So one of the first things I want to check on this model is to make sure that we have consistency of units across the output and the expected output, right? So in Simulink, we have this information overlay that shows you additional information for your signals in the model. to help you perform diagnostics. So what I can do is to turn on the unit option here. And then we can see.
I can see radians per second. Yeah.
So we can see that the unit from the output is radians per second, but I'm expecting a no-load speed of 4,000 RPM. So this clearly indicates that we have a mismatch in our units. So what I can do is that I can quickly bring a block called the unit conversion block. So what it does is that it looks at the unit of the left-hand side signal as well as the unit on the right-hand signal, and it does the unit conversion automatically. But now we're seeing, on both sides, the units are the same. In this case, we can bring in a signal specification block, which allows you to specify the unit of a particular signal. In this case, we want to specify the output signal to be in the unit of RPM. So if we just quickly type in RPM, it's providing us with a suggestion that we can use. And then we can just click apply. So now we can see that, we have selected the desired output unit for our signal. And if we quickly run it again, we can see this time as my DC motor supply voltage reaches 12 volts, the output speed of the DC motor also reaches 4,000 RPM, which is exactly what we would expect from the spec sheet.
Yeah.
So we already have a lot of blocks and connections on the Simulink canvas, right? It's looking a little congested. If I keep building on top of this model, I'm just going to get a lot more complexity that I have to deal with. So maybe there's a way for us, to improve the organization of this model. And the way to do that is to, do a multi-select on the elements that I want to group together. And then in the tool strip, I can select Create Subsystem. So Simulink has automatically grouped everything together into the subsystem. And now I have a much cleaner look of the model. And I can give it a more descriptive name.
I can also see the skeleton of the model from the top.
Yeah, so this is like giving you a little preview of what's inside of it. And so if we go inside of the model, we can see that, this is the DC motor model that we just built. And we can also specify the input as well as the output of the subsystem. So the input would be voltage, and the output would be, speed. And we can see that Simulink has automatically created the import as well as the output for me, and have renamed them to match the names that I had at the top level of my model. And let me just turn the the unit information overlay off to get a cleaner look. So now we want to move to building a controller for this DC motor. And the objective of this controller is that we want to have the output speed of the DC motor match a input reference speed. And in order to do that, we need to first specify, what is the input reference speed. And there are different ways for us to define that. You might already have some data that you have defined in, an Excel spreadsheet. You might have, already created a MATLAB variable that you want to be able to bring into Simulink for specifying your input signal. And today I want to show you a way, an interactive way that you can use to sort of customize your input signal in MATLAB, and then you can bring that signal from MATLAB into Simulink for running your simulations. So what I can do is I can open up a new live script, and then there is a live task called Create Signal. So live tasks are like mini apps that you can use in MATLAB. to perform certain tasks without writing any code. So these are very interactive ways for you to, specify your signal, and you don't have to write any MATLAB code for it. The best thing is that the code is also, automatically provided for you along with the live task, so you get the code for free. And here in this live task, we can see that there are different options for me to specify my signal. So I can just use, the insert point option for me to click on this plot as different points along the signal line. And I can also have these points being snapped to the X and Y grids to make sure I have these nice integer values. So what we want to do is that I want the motor speed to stay at 0 for a couple of seconds, and then to have it ramp up at a particular time instant, and have it stay there for a while before it goes down to half of its original speed, and then to have it stay there for the rest of the simulation. As you can see, as I'm drawing these points on this plot, there's also a table that's showing me the different X and Y values that correspond to these points that I've just added.
Mm-hmm.
And the best thing is that it's not only providing me a way to visualize the XY values, but also I can edit the values in the cells to adjust my signal. So I can just type in different values in these table cells.
You can also see on the right-hand side that Simulink has captured it in the workspace. So it has created that variable in the workspace.
Yeah, so the live task is automatically updating the signal value, and the changes are being reflected, in this MATLAB variable that's been automatically created in the MATLAB workspace. So I can click on it to give it a more descriptive name. For example, desired speed. And what's really awesome is after you have defined the signal in MATLAB, you can bring this signal into Simulink for running your simulations by using the playback block.
Tianyi, you just said that code will be generated for this. So can you just quickly show us how it can be done?
Yeah, so if we scroll down to the last section of the live task, and if we expand it by using the show code option, we can see that the code has been automatically generated for the process that creates the signal. So that's really cool. If you want to do more customization, if you want to edit the code to perform more actions, you're free to do so.
Yeah.
So we just mentioned that you can load signal data from a variety of sources into Simulink. And here we can see that there are these different options in the playback block. So I can choose to save a copy of the signals in my model. And I can also select, this create a signal variable, that I just created in MATLAB. And it's showing me a quick visualization of what the signal looks like to see if it matches what I had in my source. So now we have specified a desired input speed. And now it's time for us to get into building the actual controller. And before we do that, Ashwin, could you provide us with an overview of what a controller is and how can we go about building the controller?
Yeah, sure, Danny. So before we talk about controller, let's talk about control. So control is an act of producing a desired result. So if there is a subject that can produce desired result for a DC motor, then that becomes our controller. So in this case, there are many controllers available, but in this case, we are going to use PID controller. So Tianyi, if you double click and search for a PID, yeah, there it is, yeah. So we have a PID block in Simulink. So I don't need to model all the equations behind the scenes which are working for PID controller. Simulink does that for me. And if you click on that block, you'll be able to see that we have two different time domains, that is continuous time and discrete time. You can use them as per your convenience. And you can also see the compensator formula which Simulink is using in the background. So you know what P, I, and D are doing. So here your job is to just provide values for proportional, integral, and derivative gain, and for the filter coefficient. So Tianyi, why don't you take a guess, maybe out of infinite possibilities? Let's take a guess.
Yeah, so this is the year 2023, so I'll just put 20 for my p-value, and then I'll put 23 for the I-value, and since today is May the 25th, I'm going to use 25.
Yeah.
So I'm just taking a random guess here. So let me hit apply. And let's run the model to see what results we have. So we can see that the output speed of the DC motor is having a crazy amount of overshoot, right? 10 to the 7th.
Yeah.
So this is probably
burn
breaking the motor.
out. Yeah.
And there's no way the motor can achieve an RPM of something to the 10 to the 7th. Right?
Yeah.
But that's the beauty of simulation, because it provides you with an early view of your software and hardware integration. In this case, how is your PID control algorithm working with the DC motor? So you're not afraid of breaking the DC motor in any way, because simulation provides you with this safe playground and safe sandbox for you to try out different new ideas for your algorithm design before you actually go out into the lab and into the field to implement these with physical prototypes.
Yeah. So now I think let's make a closed loop system for our DC motor, and let's call in the subtraction block or a sum block, and then we'll change the signs.
Yep.
Yeah.
So let's try to change it from an open loop system to a closed loop system so that we have actual feedback.
Yeah. So what we are trying to do here is we are trying to calculate error between desired speed and the output speed. So, and we are supplying this error to our PID controller, which is gonna modulate our voltage and provide desired result from our DC motor. Yeah.
And we can also give more descriptive names to these signals. For example, I can just label the signal by double-clicking on it and typing in the name for that particular signal. So this would be the output speed, and this would be the input speed.
If anyone has any questions, please pop them in the chat.
So now I want to see how we have improved the performance of our controller. But before we do that, we actually want to, we're expecting to go through many more iterations on fine-tuning the controller's performance. So scope is a great option for viewing signal values from a single simulation run. But what about we want to compare values of the same set of signals from many different simulation runs? In this case, we can log the signals that we want to visualize and then use what we call the simulation data inspector to see all of the different values across multiple simulation runs in a single place. So let's just go ahead and run the simulation again. And we can open up the simulation data inspector. So we do have, the values for these signals. So we can see this is, doing a lot better than our open loop control system, because our output speed is, tracking the input reference speed more closely than before. But still, there is a lot of overshoot that's happening when the input signal is transitioning.
Yeah. So if we tune our model in a better way, I think we'll be able to solve it.
And with the simulation data inspector, I can also zoom different parts of a signal in time so that I can inspect the detailed behavior of the signal values. And I can also use a cursor to trace through the different y values along the x-axis as the y values change.
Mm-hmm.
So we can see that there is a lot of overshoot that's happening around this area.
Almost double the required value.
So we can keep, inputting these different values as our, guesses, but there's another way that we can use in Simulink to perform automated tuning of the control system, and this is what we call the PID tuner app. So if we click on the tune button, Simulink is gonna analyze the system and then provide an initial tuned response automatically for us.
Mm-hmm. So either you can keep guessing the values or try to figure out the right ones by yourself, or you can use this app. So yeah, I can see that there is already a tuned response in the graph.
So if we show the parameters of the controller, we can see that it's provided a set of tuned values for P, I, and D. And we can see that it has brought the overshoot down significantly from before, but at a slight cost of the response time. So this is the place where we can make different design trade-offs by performing manual adjustments on not only the response time but also the robustness of the control system. So we can make it go faster by using the slider here, and then we can also make it a little bit more robust. So I can update the block to reflect these P, I, and D value.
Yeah.
So now we have a tuned response that's been visualized here.
Yeah.
And if we run the simulation again and go to the data inspector, we can see that Simulink has archived the values from our previous simulation run. And what I can also do is to change the color for this particular signal to have a better contrast between what we had before and what we have now. So the blue signal is our most recently tuned response of the controller. And we can see that the overshoot is definitely, under control. And the output signal is closely tracking what we have as the input reference signal. So this is looking really good here.
Yeah. So even before you simulate your model, your PID tuner app is going to show you how your output is going to look like. So that is a great help.
Yeah, so we want you to focus on the design, not the implementation, right? Because we take care of, all of the formulas and equations underlying the PID controller block. And then we also provide you with a set of automated tools for you to change your designs very quickly so that you can go through all of these rapid design iterations without taking a very deep look inside of what's underlying the hood, right? So,
Tianyi, we have one question in the chat. How do I convert signals between Simulink and Simscape? So maybe you wanna answer them? Yeah.
Yeah. So we introduced this converter block. So that's the block that we can use to go from the Simscape world to the Simulink world and vice versa. So we have a particular block for us to go from Simscape to Simulink. So that's the PS Simulink converter. And then correspondingly, we also have a Simulink PS converter for you to go from Simulink to Simscape.
Yeah.
So now we have, built the DC motor model. We have built a controller. We have fine-tuned the control response for the controller. And now we want to show you how you can, build bigger models and more complicated models using the components that we have just built.
Yeah.
So we want to show you the Quadcopter drone model in Simscape. So this is something that you can find on MathWorks File Exchange, and you can download and play around with this example.
Yeah.
And here's
So
the model.
Now, yeah. So till now, you have explained how to create an individual component like DC motor. And now we'll be talking about how to combine these individual components and bring them together and create a entire system. So just like the windmill model which Tianyi showed, here also you can model the environment, and they have also modeled the controller, and they have given a reference trajectory to the quadcopter. And if you go inside the quadcopter,
Yeah, it's a bigger model that's taking more time for Simulink to
Yeah.
load. There are a lot of components inside of it. So here it is.
Yeah. So inside the model on the right-hand side, bottom right, you can see that there is an electrical system reference. So yeah. So inside that, this example model has 4 DC motors. So it is almost similar to the ones which we have created. But this is, I think, a different type of DC motor which this model is using. So, and if you go back, you can see that the body and the four propellers have been integrated with Simulink through their CAD models. So the Simscape multibody has used the CAD model to capture the properties into the Simulink canvas. And if you go inside any of the propeller DNA, yeah. So, and if you click on any system, maybe click on a housing or a base. Yeah. Yeah. So here you can also view the model which has been captured. So this is a great way to capture properties of your CAD model and directly use them for your simulation purpose.
Yeah, you can easily bring
Tianyi,
these, mechanical structures
yeah.
from CAD files, and then you can add sensing, actuation, and control to be able to put these mechanical structures together into a full system and be able to run simulations on the system.
Yeah. So let's run the model. Let's see how we can visualize this entire system. Yeah.
And you can also see that there is the load that the quadcopter is carrying. So what we can see here is the mechanics explorer, and it's given us an animation of the 3D simulation that we're running of the quadcopter. We can see that the quadcopter is slowly taking off from this spot here, and then it's traversing through a trajectory that we have specified. And I can increase the animation speed to make it run faster. We see that the drone has just dropped the load. It's going back to the original spot where it took off.
Yeah. So Tianyi, just to have fun, let's increase the weight of the package and see where it fails. Yeah.
So the way that I can change that is that I can go to the MATLAB workspace, and then there's a variable that's called the package density, right? So if we keep the size of the package same and then we increase the density, the load is going to become heavier. So let's just, multiply this density by a factor of 10. And let's run simulation again to see what happens. Yeah, so it seems that we have a problem here because the load is too heavy and the drone is not able to lift off.
Yeah. So it depends on how you have modeled your DC motor, how you have modeled your propellers and the body of the drone. So that will decide the ultimate limit for your drone.
Yeah. So that's the power of simulation, right? You can run these trade-off studies. You can specify different properties for your components in the system, and to sort of test out what's the limit of your system, and you can do all of this without worrying about whether you're crashing the drone into a building, or whether you're breaking these 4 motors that are inside of the propellers. So this really helps you go through these rapid design iterations without building costly physical prototypes. And
so, Tianyi, we have a question in the chat. You started presenting using voltage variable, then you converted to speed variable. Is that automatically converted? So maybe we can turn on the unit debug. In the debug section, we can turn on the unit part, and let's see how the units are converted for PID controller. So I think that would answer the question. Okay. Okay, so I think we might need an unit inertia block to showcase the unit just before the DC motor. So we can put 2 inertia blocks, one one after the PID controller and one before the PID controller.
Yeah. So we're able to specify the units of the signal. So not only just the quantity it represents, but also the units that the signal represents, right? So we just showed you, the capabilities in Simulink for you to, visualize 3D simulations. And we also have, a lot of other domain-specific tools for you to build these applications, like aircraft, vehicles, and then quadcopter drones, and then industrial robots. And you can, visualize all of these systems in 3D virtual environments. With the UAV toolbox, you can even design autonomous navigations and controls algorithms for your drone, so that the drone doesn't have to stay on a fixed trajectory. Instead, it can have its own perception of the world. It can try to navigate this virtual world on its own. And with Simscape Multibody, you can import 3D structures into Simulink, and then you can perform system-level simulations. So before we wrap the live stream up, I would like to introduce you to these resources to help you get started with Simulink, and you can also find the links to these resources in the chat. So we have a set of Simulink videos that showcase different features and capabilities in Simulink. We have the Simulink on-ramp course that we just introduced at the beginning of our live stream. So you can go through a series of exercises at your own pace to learn more about Simulink. And then we have, we showed you the Simulink product page that you can use to discover more about Simulink. And then we have the Simulink documentation that shows you a comprehensive list of different examples and blocks that you can use in Simulink. So don't forget to subscribe to our MATLAB YouTube channel, and please stay tuned for more videos and live streams that are coming up soon. This is all we want to show today, and we hope you have taken away some useful tips and tricks from today's live stream. And have a great day.
Thank you. Thank you for joining in. Take care. Bye-bye.